Morning, everyone. How's everyone doing today? Is everyone able to see their exam grades? Because unlike last time, I did not have to manually post these ones. Okay, good. Okay. A little concerned. Yeah. Okay. So really quickly, there's a teeny bit of stuff I want to talk about that's on the homework that for 15.3 that I didn't realize was on the homework because I lectured about it before I think the questions were available. So let me briefly mention a couple things. So if you have some region, so if you have a function and you want to know the average value of a function over a region, so in particular, if it's in R3, so if you have a function of 3 variables and you want to know the average value of the function over some 3-dimensional region, so if you want to know the average over some region W in space in R3, it's just the integral of the function so remember the average is if you have like n objects, it's you add up those n things, like those n scores, and you divide by the total number of objects, right? So this integral is like adding up all the objects, and then you have to divide by the total number of objects, which is just going to be the volume. Of the region, W. And remember, the volume of some region in R3 is just the integral of 1, the function 1 over that. Oh, sorry, this is a triple. So you're just integrating the function 1 over the region W, and that's the volume. So similarly, if you want to know the average value of a function of 2 variables over region D and R2, you integrate the function over D, and then you divide by the area of D. Same thing. As long as you know this formula, it should not be too difficult to do. But there is some confusion as to how to calculate the average. Also, so you're going to be asked to integrate over a tetrahedron. In particular, so basically, I'll draw a picture in a sec, but. So vertices 0, 0, 0, A 0, 0, 0, B 0, and 0, 0, C. So basically what these types of tetrahedrons are just, you take the coordinate planes and those form the sides. And then the other side is the piece of a plane, which goes through A 0, 0, 0, B 0, and 0, 0, C. It's the piece in the first octave. So if you take the region bounded by this piece of the plane and then all the coordinate planes, that solid region is your tetrahedron. So the way we want to integrate over this region really quickly is we're going to bound Z with functions, and then look at the region D in the XY plane where X and Y live. So Z is bounded below by the XY plane, right? So that's the plane Z equals 0, and it's bounded above by this plane here. So we need to figure out the equation for this plane. So let me tell you really quickly. So the trick to doing this one is first write it in the form so notice this works. The plane X over A plus Y over B plus Z over C equals 1. Right, notice that works for all 3 points we have, A 0, 0, 0, B 0, 0, 0, C. Right, you plug in X equals A, Y equals 0, Z equals 0, and you get A over A plus 0 equals 1. And then similarly for 0, 0, B, or 0, B 0, and 0, 0, C. So it's kind of a nice shortcut to figuring that out. And then from there, just get Z by itself. And those are our bounds for Z. Okay. So then we need to figure out where D is. Well, D, remember, is just going to be the easiest way. You can just directly draw a picture of what D is in the XY plane. Right, notice if you just look at the shadow of this region on the XY plane, if you just smash this directly down onto the XY plane, we get this region here. And so on the x-axis, we go along by A, y-axis, we go along by B, and we get that guy there. Oh, sorry, I mislabeled. Yeah, this should be B and this should be C. Sorry. I mislabeled these. Yeah. Good eye, Ariane. But any questions? I don't have time to do an example of this, but yeah, it's still a part of the homework. The homework is due tomorrow, right? or Wednesday, one of those. Wednesday, okay, yeah, that should be enough time to do this. It's still a part of the homework. Okay, so I hope that's enough. If you still have questions, I have office hours tomorrow. But yeah, so I want to move on to today's intended material. So I believe that is 15.4. So last time we talked about integration in polar coordinates. Today we're going to talk about integration in cylindrical coordinates. Which is actually not anything new. So cylindrical coordinates are basically just so we're going to use cylindrical coordinates. And in fact, we could probably get away with not having this whole section, but it's still useful to have the practice. But so basically, Z is going to be bounded above and below by functions. Of X and Y. So Z is sort of the normal variable, but X and Y are going to live in a polar region. Oops. So what I mean by polar region is a region best described by polar coordinates, right? A polar rectangle, something bounded by Piso's circle, essentially. So for instance, if you had suppose Z lies between Z equals 1 and Z equals 5. And then say X squared plus Y squared less than or equal to 4. So X squared plus Y squared less than or equal to 4. So that's X squared plus Y squared equals 4 would give us what kind of surface? Correct, but in R3, what kind of surface would it give us? Right, it would give us a cylinder centered at the z-axis of radius 2. If it's less than or equal to 4, it's a solid cylinder, everything inside of there. So basically we get, so this is z equals 5, this is z equals 1. We get this solid region here. So Z is bounded by Z equals 1 and Z equals 5. But the X squared plus Y squared less than or equal to 4, if we look at the region D, where x squared plus y, or where x and y live. So this is our region D in the xy plane where x and y live. This region is best described using polar coordinates. Right, and polar coordinates, this would just be a polar rectangle. R would go from what to what here. So remember, R is the distance from the center. So all the points in here, what's the closest we get? Sorry, to the origin. What's the closest we get to the origin on this region D? The origin itself, which is 0. And the furthest away we get is distance 2. The outer circle is just R equals 2. And then theta goes from what to what? What's the smallest angle we make with the positive x-axis? The largest? Well, it goes from 0 to 2 pi. So that is essentially cylindrical coordinates. Z is just going to be Z. But x, instead of having x and y, we have r and theta. So points in cylindrical coordinates are going to be of the form r theta z. Suppose that's our point r theta z. So z is just going to be the same thing. Z is just the normal z from rectangular coordinates, right? It's just how far along the z-axis do we go. And r and theta are going to work exactly like they do in polar coordinates. So we're going to project this down to the xy plane. So r is going to be the distance when you project it down to the xy plane from the origin. And theta is going to be the angle measured counterclockwise made with the positive x-axis. So when you drop it down to the point when you take z down to 0, bring it down to the xy plane, r and theta work the same as they do in polar coordinates. And so we still have the same formulas. X is going to be r cos theta, and y is r sine theta. And then we have the related x squared plus y squared is r squared, which you could derive from x is r cos theta and y is r sine theta, but it's good to remember. Okay. Does that need any more clarification? Was it clear how R and theta work? Okay. So the way we're gonna integrate here is also nothing new. So suppose z is bounded between, so now basically the only difference is, so normally if we integrate over a region of this type, where z is bounded by functions of x and y, and x and y live in a polar region, what we would normally do is we would integrate our function z first because it's bounded by functions. It's bounded below by z1 of xy and above by z2 of xy. So we're going to do our triple integrals. Whoops. Function of x, y, and z. We would do our integral like this. We would first integrate with respect to z. Z goes from z1 of xy to z2 of xy. We've integrated with respect to z. Now we have a function just of x and y, a function of two variables. And we integrate that over the region D, where x and y live. So when we integrate over D, we see that it's a nice polar rectangle. So then we would switch to polar coordinates. And then we'd introduce r and theta at that step. The only difference between that and what we're going to do is we forget about x and y right away when we do cylindrical coordinates. So right away, instead of writing the upper and lower surfaces as a function of x and y, we write them as a function of r and theta. Basically, you just replace x with r cos theta and y with r sine theta in the equation of your surfaces. So this is our region D. R goes from A to B, and theta goes from alpha to beta. So this is our region D. The way we're going to integrate over this is, sorry, not D, let me say W. So we have a function f of x, y, z. We want to integrate over this region here. Then what we're going to do is we're going to integrate first with respect to z, because it's bounded by functions. So z goes from z1 of r theta to z2 of r theta. And notice we're integrating a function of x, y, and z here, but our variables are r theta and z. So we have to do the change of variables here. We have to use these guys. Z stays z, but x Every time we see an x in the function, we replace with our cos theta, and every time we see y, we replace with our sine theta. X becomes our cos theta, y becomes our sine theta, z becomes z. So first integrating with respect to z. But remember, when we did things here, first we integrated with respect to z, and then d was a polar region, so we switched to polar. And what is dA when we integrate in polar? So when we're in rectangular, dA is just dx dy or dy dx. What is dA in polar, though?
Is it the r dr d theta?
Right. And we have to do the same thing here. So z is just z. There's no change of coordinates there, so that's still the z. But we have to multiply everything by r, dr d theta. So this whole thing is our dv, the r dz dr d theta. So then r goes from a to b, and theta goes from alpha to beta. So you can't forget that r here. So honestly, if we never went over this section, you should still be able to do these integrals. Like this. Just say, okay, z is bounded by these guys, and then after we integrate with respect to z, we switch to polar for the integration over x and y. And it works exactly the same way. This, it just gets everything done in one step. Which may or may not be more convenient for you, but yeah. Okay. So for example, suppose we wanted to integrate function z over the region w with respect to volume, where z, I'm sorry, so let me just describe w. So in w, z is going to lie between z equals 0 and z equals y. And x squared plus y squared is going to be less than or equal to 4. This is where I wish my artistic abilities were a little better, but let's attempt this here. Okay, so z equals y is going to be a plane which goes through the origin. Let me see if, so that's our plane. Z equals y, bounded below by z equals 0. and we lie inside the cylinder x squared plus y squared equals 4. So kind of hard to see all this here, but let's see if we can't figure things out here. Okay, so we already have explicitly our bounds for z. Z goes from 0 to y. Now we need to figure out our region D, where x and y live. We need to figure out what r and theta are. Okay, so if you're a better artist than me, you might be able to figure this out from the drawing. And if you look in the book, you can kind of see what's going on here. But so initially, so we know x and y have to lie inside x squared plus y squared equals 4. All right, we know x squared plus y squared less than or equal to 4. So we know x and y live inside that region in the xy plane. But are we getting the whole thing? Well, not quite, because up here, we know z lies between 0 and y. And so this inequality implies that y has to be greater than or equal to 0. Right? If z is greater than or equal to 0, but less than or equal to y, then y has to be greater than or equal to 0. So we're only getting the top half. Of this circle in the xy plane. This one's a little tougher to see. But any questions about where our region D comes from here, where x and y live? So we're going to get our bounds, right? We already have z goes from 0 to y. Those are our bounds for z. Except, remember, in cylindrical coordinates, there is no y. So we need to change y to its equivalent in cylindrical coordinates. What is y equal to in cylindrical coordinates in terms of r and theta? R sine theta, right? And then we go to r and theta, right? Where x and y live. It's this polar region here. So r goes from what to what? The points in this region are, what's the closest we get to the origin? Right, we get the origin itself. And the furthest away we get is 2. Right, so this is, the outer circle is r equals 2. Set up all points which are distance 2 away. And then theta, the smallest angle we make with the positive x-axis is, of course, 0. What is the largest angle we make with a positive x-axis? Pi, right? And so those are the bounds for our integral. So let's plug it in. So we said z goes from 0 to r sine theta. R goes from 0 to 2. Theta goes from 0 to pi. And then z is a function of x, y, and z. And so we need to switch to cylindrical. Well, all that shows up is z. And remember, z is just z in cylindrical, so the function's not. But if it had x and y, then we'd have to change x to r cos theta and y to r sine theta. So dv becomes, remember, r dz dr d theta. And so let's do this integral. Okay, so we're integrating z times r with respect to z. So integrating with respect to z means everything but z is a constant. So r and theta become constants. So zr becomes 1/2 z squared times r, evaluated from r equals 0, z equals 0, up to r sine theta. So we get 1/2 r sine theta squared minus 0 squared times r. And putting this all together, we get 1/2 r cubed sine squared theta. So I'm going to go through this quickly. Plugging this in. Oops. So we get the integral. Theta goes from 0 to pi, r goes from 0 to 2 of 1/2 r cubed sine squared theta dr d theta. Looking at this inner integral, integrating with respect to r. So 1/2 r cubed sine squared theta. Theta is a constant. So the r cubed becomes r to the 4 over 4. So we get 1/8 r to the 4 sine squared theta, evaluated r equals 0 to 2. When we do that, we just get 1/8 times 16, so 2. We get 2 sine squared theta. So plugging that in, theta goes from 0 to pi of 2 sine squared theta, d theta. So this is a good thing to remember. So if you remember back to 141, recall how we do the integrals of sine squared and cos squared. This would be good to remember because they're kind of unavoidable later on. But try to remember these identities. So remember, sine squared theta is going to be 1/2 times 1 minus sine 2 theta. Oh, sorry. 1 minus cos 2 theta. And then cos squared theta is going to be 1/2 1 plus cos of 2 theta. Let me just make sure. Yeah. Okay. Yeah. That's right. Okay. So those would be good to remember. If you can. So remembering those two identities. So using that, 2 times sine squared theta becomes 2 times 1/2 times 1 minus cos 2 theta. So the 2 and the 1/2 cancel. We get 1 minus cos of 2 theta d theta, which is just theta, minus 1/2 sine of 2 theta evaluated theta goes from 0 to pi. And so we just end up getting pi. So we get pi minus 0 here, and then sine of 2 pi is 0, sine of 0 is 0. And so we get nothing from that. But the whole evaluation thing is whatever. These would be good to remember, but it's pretty straightforward from there. The important thing is just setting up the integral. Okay, so in the interest of time, rather than evaluating some integrals, let's just take an integral, some integrals in rectangular coordinates and turn them into integrals in cylindrical coordinates. So we're going to rewrite the following integrals using cylindrical coordinates. So suppose we have z square root x plus 4y squared plus y squared dz dy dx. So z is going to go from 0 to 2. Y is going to go from negative 1 minus x squared square root to square root 1 minus x squared. And then x is going to go from negative 1 to 1. Okay, so what we're going to do is finding the bounds for z and cylindrical is really easy. You're given the bounds. Z goes from 0 to 2. You're just going to change those to cylindrical. So every time you see an x, you replace with our cos theta. Wherever you see y, you replace with our sine theta. Well, there's nothing to do there. So that's easy. For x and y, you're going to want to draw a picture in the xy plane. So we're going to do that to find the r and theta bounds. Okay, so y goes from negative square root 1 minus x squared to positive square root 1 minus x squared. So y equals negative square root of 1 minus x squared. That's going to be the lower half of the circle, x squared plus y squared equals 1. And positive square root x squared plus y squared is going to be the upper half. That's the lower half. This is the upper half. Does everyone see that? Right, so if you have y equals square root 1 minus x squared, if you square both sides, you get x squared plus y squared equals 1, right? And since it's positive square root, you only get the part where y is positive. This negative square root 1 minus x squared is the bottom half. So y goes from that lower guy to the upper guy, but we may not necessarily get the entire circle or the entire disk inside that circle. It depends on x. So if x just goes from, say, like 0 to 1, we would get the right half of this. But here x goes from negative 1 to 1. So we get the entire circle. Does everyone see that here? Okay, so this is our region, D, where x and y live. Easily described as a polar rectangle, clearly. R goes from 0 to 1, and we get the whole circle, so theta goes from 0 to 2 pi. Okay, so let's rewrite our integral. So z goes from, we said 0 to 2. We've already changed the polar, nothing to do there. R goes from 0 to 1. Theta goes from 0 to 2 pi. Okay, now our function z times square root x squared plus y squared. When we change to cylindrical, what does that become? Well, z becomes z. And what is square root of x squared plus y squared? So x squared plus y squared is what in cylindrical? R squared, right? The square root of r squared is just r. And so that whole function just becomes z times r. And then when we change to cylindrical coordinates, remember this whole thing is dv. Our dv is r dz dr d theta. So let's just multiply everything by r. We get z times r squared. And that's our integral in cylindrical. So z bounds you get directly from the z here. You just change x to r cos theta and y to r sine theta. And then for the r and theta bounds, you look in the x and y bounds, you draw the picture of that region. You should be good at doing that now. In the xy plane, that's going to give you a polar region, and then you use polar coordinates to find r and theta. Let's do one more example. suppose x goes from 0 to 1, y goes from um, 0 to square root 1 minus x squared. And z goes from 0 to x squared plus y squared. And who cares what the function is? Okay, so our z bounds. So z goes from 0, nothing to do there, no x and y to replace, to x squared plus y squared, but we want to write this in cylindrical coordinates. So in cylindrical coordinates, what is x squared plus y squared? Well, we've already said it. That's our r squared. And so really quickly, let's draw our region where x and y live, and then figure out what r and beta are. Okay, so y goes from 0, y equals 0, which is just the x-axis, up to y equals square root 1 minus x squared, which remember is the top half of the circle of radius 1. Pretend that's the top half of the circle of radius 1. So that's y equals square root 1 minus x squared. Y equals 0 is just the x-axis. So x is going to tell us how much of this top half of the circle we're getting. If x goes from -1 to 1, we get the whole half circle. Kind of an awkward way to say it. But x is only going from 0 to 1, right? So we go from x equals 0 up to x equals 1. And so we get the right half of this guy. So we get a quarter circle here. So r is going to go from 0 to 1. This outer piece is bit is the piece of the circle, r equals 1. And theta is going to go from, well, the smallest angle we make is 0. And the largest angle we make is what? Pi over 2. And so we're going to plug this into, plug our bounds in here. So theta goes from 0 to pi over 2. R goes from 0 to 1. Z goes from 0 to r squared. F of x, y, z, replace x with our cos theta, y with our sine theta, and z with z. And dv becomes r dz dr d theta. Okay. So, if you don't have any questions, I will see you guys either on Wednesday or during office hours on Tuesday. And have a great day, guys.